Good morning.
Morning, Doug.
How is everyone today? It's a good rainy day, good day to be inside and get smart. Listen to some tunes, learn how to take an integral. Oh, baby. Awesome. Let's see. Didst anything damage your person from your homework last night that you would like to ask about before we deepen our grasp on trig substitution? Well, then, let's start off kind of slow and 8.4 trig substitution. All right, I'll turn the radio off. Let's start off with something kind of cool. You all know that can never go back to regular pencils again. Perfect circle has just been drawn, my friends. You all know that the area of that circle is pi times radius squared. And again, there's just a lovely history of the Greeks trying to figure this stupid shape out. Circles are really kind of a beautiful, neat shape and so practical in so many ways and so many applications. But to find the area of it was a tremendous mystery. And I unveiled a little bit of that to you early on in calculus when we talked about limits and how to think of that as like a 20-sided shape and then find the area of that, but then let the number of sides go to infinity. And so that the concept of a limit. But let's take now that we're sort of steeped in limits, let's take a look at, let's build this formula for ourselves using calculus. As I mentioned, if a calculus teacher is kind of honest with you, there aren't a whole lot of reasons to do calculus for practical people because we have machines that kind of take care of that for us, which again, I think is wonderful. And the main reason is just because calculus gives us formulas. And so the formula for the area of a circle is thanks to calculus. And you're now in a spot, thanks to a little bit of trig substitution to produce that. So let's see if we can actually produce this. So if I came in here and stuck this circle on a piece of graph paper like so, and I'm just going to find the area, and I want to give you a second to think about this. If I put it right there, and I thought of this circle as having a radius of r, thus, as you know, its equation would be x squared plus y squared equals r squared. So that's the equation of that circle. And I said to myself, I would like to find the area of this circle. And I'm going to make a slice like so. And I'm going to slide that slice all the way to the right, all the way to the left. And I'm just going to find that quarter of a circle up there so that I can just multiply this by 4. So the question is, can you write an integral? Can you write the integral thinking of r as a constant? R is a letter, but it stands in for, a circle of radius 10, a circle of radius 20, whereas x and y are actually variables. Can you, from your calculus skills, walk away Can you write a formula? One of the best ways to think about this is that is one of the many points x, y that make up this circle. And those have to be variables because I got to have that slide. At that point's got to move. So add up all those rectangles. What's this? I hope you think this is, I don't know if I want to say easy, but let's just say satisfying. Like, oh yeah, I can do that now. That's pretty cool. So since to get to that point up there, I obviously have to go over x, ding, 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 and up y, boom, 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 boom. Then that rectangle's size would be y for height and a little bit of x for width. So there's the area of the rectangle. And now, if I just let x be a variable and slide everywhere I want it to slide, then I'm good to go. And since I'm, if you will, stuck with x, since there's a dx, and again, you're not actually stuck with x. I won't belabor this point, but if you took the derivative of your line of your circle down here, isn't it the derivative of x squared is 2x dx, and the derivative of y squared is 2y dy, and the derivative of r squared is nothing. As I said, r is a constant. There's a conversion right there between dx and dy. If you actually wanted to switch that dx to a dy, you could totally do it. But it's easier to switch y out. So if I work with x, would you agree I need x to go everywhere from here to here, which is everywhere from r to 0? Now, I still don't think you should be able to do that easily. But I would say if you can't write that out now, especially after we've, rotated, we've taken that shape and made it three-dimensional and rotated it around and so forth. If you can't do that, you're behind. Like you're missing the conceptual understanding of calculus to not be able to say, it's just a rectangle. Like write the equation for the rectangle, y times dx, and add them all up. And it's the beauty of what an integral is. And of course, if you solve this equation down here for y by subtracting x squared away from both sides and then taking the square root, then you have a way to get rid of that one y term. Remember, we're all excited in substitution when we get an integral that has all the same letter in it. So now we got all x's, awesome. So bam, we're ready to go. So now we can say this baby is 4 times the integral of r to 0 times the square root of r squared minus x squared dx. We're ready to solve that integral. And true to what we just started studying last time, that's not an easy substitution to make. If you let u be r squared minus x squared or something of that nature, it's going to go nowhere. Do you see the Pythagorean theorem in that statement? Further, do you actually understand that Pythagorean theorem is the reason we even have an equation for a circle? I think I'll erase this because my figure is so beautiful, but isn't there a right triangle there with x and y and r? And if you just simply write out the Pythagorean theorem, like that is the equation for a circle. That's the relationship between those sides. And so in a sense, Pythagorean theorem and circles they're pretty good friends, you might say. And so the substitution that you need to make for this problem, because you're not going to be able to solve it. Remember I said yesterday, one of the intuitions I hope you gather is, hey, look, there's an x squared in there. It is really a bummer that there's not an x outside, because then I could let u be r squared minus x squared, because the derivative of which would produce an x, and then it would cancel that x, and I could just use that substitution. But this chapter exists because there are wonderful problems like this, and this is, in my mind, one of the best ones there is, in the sense that like this is a good reason to kind of understand trig substitution. You are not going to get this substituted correctly unless you understand trig substitution. And again, our goal here is to produce, an epic formula. in all of math. I use that all the time in construction for calculating volumes of concrete that are circular. Very practical formula. And so, can you see the Pythagorean theorem in these problems, in all these problems? And perhaps after trying some other substitution that didn't work, but when you see the Pythagorean theorem looking like this, can you see that, well, you know, because r squared is the positive one, r would have to be here, and then x has to be one of these other two sides. Notice all I'm doing is reproducing the same right triangle that was sitting over here in this case. That doesn't usually happen, but that's kind of what's happening here. And so what we noticed yesterday was an amazing substitution comes by just looking at the fact that the Pythagorean theorem of the square root of r squared minus x squared hints at the fact that, hey, trig is involved in right triangles. And so trig substitution comes into play. So if I said I'm going to make that angle theta, then I could say that the cosine of theta equals adjacent over hypotenuse. That's your substitution. This is the crowning jewel of this section, being able to create this substitution. Let's make it go bam so that it sticks in our brains a little bit better. That's my substitution. Now I can do anything I want to it. I could multiply both sides by r. I could take the inverse code. I mean, I could do anything I want to that shape, but really that's my substitution right there. So I get, let's see, I want to substitute that for x. So I guess I find myself thinking that would mean hence that x is equal to r cosine of theta. And now I'm ready to rip. And while we're at it, let's make the derivative. So the derivative of x is the derivative of x. Remember, r is a constant. So this is not product rule. Thank God, that'd be awful. R is a constant, so it comes along for the ride. The derivative of cosine of theta is sine of theta times d theta. And I usually don't write this out because I assume you can see this. Well, I guess it's okay. So in a sense, we get kind of lucky here because that's already solved for dx. And so now I'm ready to transform this thing. There's a 4 out front. I can now rewrite my integral as r squared minus our new value for x, which is r cosine of theta squared, which again, as I mentioned yesterday, these problems are going to get worse before they get better. Your gut reaction to that should kind of immediately be like, uh-oh, that isn't good. And then you go replace dx and you replace it with r sine of theta, and you think there is no way this is a good idea. That's better than what we had before. This just does not look possible.
Real quick, should that be a negative sign of theta for the
Derivative of cosine is negative sine. Thank you for rescuing me. Thank you, Cheyenne. So that's actually a negative. I guess I'll throw it out front.
Why aren't we dividing the negative r sine theta from d theta?
Yeah, that's a good question, because I need to get rid of dx, and because of the weird nature of the substitution I made, does it make sense it was like already solved for dx? So every other time we've done this, we've always kind of needed to solve for d theta, but it's dx that I'm trying to replace. Remember, I don't want any x's. So oddly, because of the weird substitution we made, it was already solved for dx up here.
Okay.
Glad you asked that. So again, would you agree this looks like we're heading into the forest here? This is not good. Interestingly, it's like, you know, the area of a circle is pi times the radius squared. So somehow this is going to turn into pi times radius squared, but notice there's no pi's in it, which is kind of weird. So let's continue a bit and let's replace the limits of integration too. So notice for our limits of integration, we said x was equal to r. So this is our equation right here. So if x was equal to r, then we'd have r equals r cosine of theta. R divided by r, which is 1, is equal to cosine of theta. Who can tell us, where am I in the unit circle? Where am I in the unit circle if the cosine of theta is equal to 1? What?
0.
Is that
Yeah, cosine is
Cosine's an x coordinate, so if it's equal to 1, isn't it the vertical? Is that pi on 2?
No, you're thinking
Or
y
is it
when
equal
you
to-
said that. You're thinking
Oh, so
y.
it's pi.
So it's either, no, it's not. There's only one answer. So cosine is the x coordinate. So the only place an x coordinate is 1 is over there at 0, as I heard one of you say. I'm just giving you time to think. Now, again, is there anything wrong with getting your calculator out and saying inverse cosine of 1? If you do that, your calculator is going to say 0. But it's kind of cool that that comes out as an exact answer. So basically, for our upper value, if x is r, that means theta is 1. And so that's kind of crazy. So that means that's a 1 up there. I'm sorry, 0. I just got done saying I can't function. At 0 degrees, you get cosine of 0 is 1. And so that turns into a 0 up there. Sorry about that. Right? Cosine of 0 is 1. And then the other answer was when x was 0. And so if I get x is 0, then I have 0 equals r cosine of theta. Divide by r, I get 0 equals the cosine of theta. Cosine of theta is an x coordinate. Where do you have an x coordinate of 0? X is 0. Now's your time, Eve. That guy right up there. Or interestingly, down here too. I wonder if it matters which one I pick. Both of those have an x coordinate of 0. I'm going to pick the simpler one, pi over 2, but I'm actually guessing that no matter which one of these I pick, I'd get the same answer. Actually, now that I think about it, given that I'm sort of saying I'm going to work with the first quarter of the circle right here, and that fact that that puts me up here, I think maybe it has to be pi over 2, since I said I'm only looking at the first quarter of the circle. And by the way, from the project, remember that because you solved this, technically there's a minus or a plus in front of this. So the fact that there's a plus here means that represents only the top half of the circle when I solved it for y. Again, these are some of the technicalities. And so that happens when theta is pi over 2. And so that's kind of cool, if you will. So it needs to get worse before it gets better. Well, this is terrible, but it's going to get better from here on. So let's start playing around with this. So let's see, I've got -4. I want to go slow here so you can see this. Do you see the brilliance of the substitution that we made start to unfold? Because if you have r squared minus r cosine of theta squared, that would be r squared cosine squared theta times r sine of theta d theta. Notice the minus sign is not inside the parentheses, so it does not turn into a positive number. And then can't you factor out an r squared from both of those terms, leaving 1 minus cosine squared? If you did not see it before, you should begin seeing it now. Times r sine of theta d theta. It's way too crowded for such a glorious concept. And r is a constant, so I can take the square root of r squared. It pops out here as an r, which means I can just take it all the way out front. And then there was another one over here. There's another r over here, so there's actually 2 r's out front, so I'll just get those outside. And what's, if you didn't see it before, what's incredibly wonderful about that statement right there?
You can replace it with sign.
Yeah, 1 minus cosine squared, the identity is sine squared. And that just took two terms. And that's the beauty of the substitution. We don't like that minus sign. That was killing us. And by that substitution, we were able to replace that not with two terms, 1 and cosine squared subtracted, but just sine squared. And now you can take the square root of sine squared and you get sine. That is amazing. That was an r squared out front. So negative 4r squared. So this is now just the sine of theta, and there's another sine of theta. And so it actually is getting better. But notice this is not easy. This is not an easy problem by any stretch. And I happened to do this one the other day. But since I already did it, let's not do it from scratch. I'm going to go, well, cheat this time, and I'm going to go look at the integral table because I don't remember what the integral of sine squared is. I'm looking for a title that says trig expressions, trig functions. Bam, there it is. So there's our answer. I'm suddenly remembering our conversation about it. So for us, since we're not using x but theta, it's theta over 2 minus 1/4 sine of 2 theta. But remember, even that problem, the integral of sine squared, was either a substitution because sine squared also has an identity, 1 minus cosine of 2 theta over 2. Or in class, if you remember, we were surprised, or at least I was surprised to discover we split sine times sine, and we did integration by parts since it was two things multiplied together, and amazingly that worked, which was really cool, I thought. X over 2 minus 1/4 sine of 2x. X over 2 minus 1/4 sine of 2x. Now we can evaluate that, my friends, from 0 to pi over 2. Let's make a little more space so we can fit that fact in there. 0 to pi over 2. Again, this is hard, isn't it? Like, it's amazing how much stuff you have to know to pull this off, but this is amazing because the end result is area equals pi r squared. I mean, that's amazing. This is going to turn, this statement is going to turn into pi r squared. And then now for the rest of history, no one ever has to do this again. We have an algebra formula. The tracks were laid. And so you were actually taking advantage of calculus all your life whenever you were introduced to this formula and you didn't know it. And now you're in a spot where you can actually make that formula for yourself. Okay, so let's start plugging stuff in. Woo, you got to be careful with this bad boy. You got to think about where you are in the unit circle. And again, let's just kind of remind ourselves of some trig. So we're not going to, and notice in this case, this is kind of interesting because I often let you punt and I'll say, use your calculator to evaluate this integral. But we can't here because we're using r as our constant. We're not picking a number for the radius of the circle. We want a formula so we never have to do this again. So we don't have a choice. Like, we can't get a calculator to tell us this answer. So let's see. So we have a negative 4r squared out front. And now let's put 0 in. So we get 0 over 2. That's very nicely just 0. And then you have minus 1/4 sine of 2 times 0, which is 0. So what is all that? What's the sine of 0?
Pi.
Zero degrees or 0 radians is here. You don't have a choice. That's where you are. And what is the sine of that angle telling you? And again, you got a calculator, type sine of 0 in, but you need to be able to think more deeply than that about trig, especially in this section.
Yeah, it's just 0 because sine is the y coordinate.
Yep. Sine is reporting the y coordinate of that point, which is 0. So that's kind of cool because that means stuff is going away. So this is 0 and that's 0. And then now we go plug in pi over 2, which is where we're actually going to get some kind of interesting answer to this, I assume. So then it's always a minus. So now I put pi over 2 in. So I have pi over 2 over 2. So that's pi over 4. Do you see some things you're starting to like? Notice what's out front. R squared, that's good. And pi over 2 is pi over 4. So notice the 4 cancels. Starting to look like pi r squared. That's kind of exciting. And then we also have, and I guess I'll kind of put a parenthesis here because it's minus everything, minus 1/4 sine of 2 theta, 2 times pi over 2. Close that parenthesis off. Close the gigantic parenthesis off, which is what 4r squared is being multiplied by. So pi over 2 over 2, of course, is pi over 4. But what's the sine of 2 pi over 2? Well, that's pi. So this is really just pi. What's the sine of pi? Hi, guys. As you should know, pi is right there. And again, sine is the y coordinate of that point, which is also 0. So that's kind of cool. This whole thing just goes to 0. So the only thing we have then for our negative 4r squared to be multiplied by is a negative pi over 4. Bam. Negative times a negative is a positive. 4 divided by 4. For now on throughout history. Thanks to trig substitution, thanks to integrals, thanks to infinitely small rectangles, thanks to an understanding of trigonometry in the unit circle. Thanks to all of those things, we get this algebra formula that we can now kind of give to humanity, and they don't have to understand any of this stuff now. Even it's one of the first algebra formulas you ever see as a student learning math, where you learn that you can, R is a variable and you can plug in R is 2 or R is 6, and that formula works for every single circle in the universe. And so, you know, that's the area of all circles. You now have the answer to the area of all circles. And so it's really cool that you can just plug in different numbers for R and out pops the area of each of those individual circles. And it's just crazy that you actually have to know as much as we know. I would highly, just as a point of it being cool as a human being, I would encourage you to try to recreate that yourself. Notice that took us a solid page. If I would have written smaller, it's like a page and a half. It took me to pull that off. But just as a point of being a human being, as an application to calculus, to be able to do that for yourself, you'll never find anybody that you can show it to that'll sit there long enough, and it's too confusing. Like, they'd actually have to know calculus to even follow what you're saying. They just wouldn't even be able to listen and pay attention. But just the fact that you can make that for yourself, as I've often said, I just love that feeling of being able to make something that I need for myself instead of just have to buy it from other people.
Can we look real quick at where you wrote x equals r? Because I think I stopped paying attention real quick, and then I came back and that was written down, and I wasn't sure where it came from.
Yeah, so back in the original problem, we said, let's evaluate this from r to 0. And because we're working with x's, by implication, we're saying x is going to be r and x is going to be 0. So then when we said, hey, let's go to theta land, well, then we're going to have to replace those out. So I came down here and said, okay, well, if x is r, then what's theta going to be? So I took this is our translation from the world of x to the world of theta. So I took that equation and I wrote it down here, r cosine of theta, except for I said it equals x, but now x, we're saying x is r. So then I divided both sides by r, I got cosine of theta equals 1, and I realized, oh, theta is 0. So in x world, if x is r, then in theta world, theta would be 0. Now, if you stop and think about that, notice that makes perfect sense. because if the X distance right here, notice what's the X distance right here? It's not very long, it's short. But right here at theta equals 0, isn't X R? Notice that's kind of cool. Like you can actually see that in the picture. It isn't just algebra. When theta is 0, X would be R. When theta is pi over 2, think about that. When theta is pi over 2, what is R, which is the X distance? It's actually 0. So you can actually see this in the circle, which is kind of cool. So I kind of had, if you will, no, that's not the right color. Let's go pink. I kind of had two problems here where I figured out what our new limits of integration were.
So if we were solving for, y, would it be r sine theta?
Yeah, and back in this problem, I could have chosen to put theta up here if I wanted to as well. So if I put theta here, then it would have been r sine theta, and it would have worked just fine as well.
Oh, you could even do it for x. You could do x equals r sine theta as long as x is over r.
Yep.
Okay, I just wondered why we chose cosine. Didn't know if it had to do with that.
Yeah, actually, it was totally random because and actually it wasn't totally random because I was thinking back to this right triangle and I was thinking x is the horizontal, so I thought let's put it here. But had I put x up here instead, just randomly, then I could have said, oh, okay, sine of theta is x over r, and it would have been just fine. If I could have, and just without actually doing it, does it make sense if that's the case? Then you would have had r squared minus r sine theta, and then this statement down here would have been 1 minus sine squared, and then you would have said, oh, that's cosine squared, and then you would have taken the square root of cosine squared and got cosine, and this term out here would have also been cosine, so we would have ended up with the integral of cosine squared, and we still would have got the same answer.
Gotcha.
It's a fabulous question. I think, were you saying something as well, Cheyenne, or somebody else was saying something?
Oh, I was just saying that that explanation made sense earlier.
Now, again, for you to even follow that statement, if you actually followed what I just did and actually understood it, that's pretty darn impressive, because you actually have to be awesome at Math 112, which most likely for the best case scenario for you was last spring, right? So it was 8 months ago. And unless you had trig on board so comfortably in your mind, then probably you did not exactly follow what I just said, right? Because I said things like, what's the cosine of, or what's the sine of pi over 2, or what's the cosine of pi over 2, and you're like, I don't really remember, and I got to think about that. And then of course I just did a bunch of substitutions. There's algebra everywhere. I mean, I tried to go slow enough to give you a chance to think, but as I said, this is an amazing culmination of everything you learned. And so to go back over this and try to recreate it, I mean, you got my note sheet, so start with a blank piece of paper and just try to create it. Number one, that teaches you a lot. But number two, then you actually made it for yourself. You owned it now. You now own this formula too. You're most likely borrowing it. You're seeing, hey, look, Doug owns that formula. Good for him. But you can own it too now. You're actually close enough that you can own this too, but probably not. Probably there's none of you who could sit down with a blank piece of paper now and recreate what I just did without running into a couple of snags. And when you run into those snags, those are awesome learning opportunities. So that's why I'm saying I would recommend you do it, because it'll make you relearn trig a little bit. And obviously you can cheat and look at mine when you need to and get stuck, or ask why did he get that answer and so forth. So it's interesting how simple that looked right there. That looked like such an easy problem. And do you understand, like I had to be really careful, or books have to be really careful to never give you a problem that looks like that too soon, because this is terrifying. This is horrible. And our substitution, unfortunately, didn't even entirely get us out of the woods, because our substitution led us to the integral of sine squared of theta. And we saw it in class the other day, and I made this problem shorter because I just gave us the answer from the other day, but the integral of sine squared was yet a further substitution, wasn't it? Or it was integration by parts. And so I would encourage you to try to recreate that too. See if you can do the whole thing. It's amazing what that will teach you and grow your intuition. And as I said, or as I've said a little bit, I'm teaching almost the same thing in engineering right now. I just showed them yesterday the project that you just got finished with, where we looked at all the forces that were pushing that wall over. And I kind of did the calculus part of that with you just because it's an application that you wouldn't understand very well. But in that class, and again, when are they taking that? Those students were in this calculus class last year. And then now 1 year later, here they are doing integrals. So it's a year later that they're sitting there, me wanting them to understand this exact concept that I'm teaching you. And so if you don't develop a conceptual understanding of it, it's going to be very hard to apply it to something. So for me to teach engineering has just been fabulously, I don't know, confirming, just because you're actually using this stuff for something real. And so it's really fun. Okay, all I want to do now is just give you practice in more easier questions, and just more, kind of practical questions that you might see in your book. So I'm actually looking at your book. This is page 544. I'm just going to pick random stuff here. So let's just do some examples. And I'm going to try to give you, and actually I would encourage you to interrupt here a little bit and just tell me. I want to try to give you enough time to either get yourself stuck or maybe, just flat get it. So I'm going to try to pick something that doesn't look like anything that we've done. Yeah, that one looks pretty ridiculous. This is question 27. So, and it's actually a definite integral, which I find interesting. And they said, let's evaluate this from 1/3 to 0. That's kind of interesting. And their equation has a 9x squared plus 1. So do you recognize that as a Pythagorean sort of statement? But then oddly, it's raised to the 3/2 power, which part of me is sort of terrified by. And they actually wrote the dx on top up here, since there's a 1 up there and you could kind of multiply it up there. I get that, but it just looks weird, so I can't do it. I got to write it out here. Notice though, the Pythagorean theorem, because what does this 2 down here represent? That's a square root. And so this is really the square root of 9x squared plus 1, and then cubed after that, right? So that looks like Pythagorean theorem. So I'm going to give you a minute. Knock yourself out. Can you make the proper substitution? Can you draw the right triangle that is represented by 9x squared plus 1? On a test, I would probably give you a question like this, and I would say use trig substitution to solve this problem. Does it make sense? That's a nice hint for me to give. I'm saying use trig to do it. That's a nice hint because setting u equal 9x squared plus 1 is not going to get you out of the woods here. I'm going to go a little bit into this and make sure you made the right substitution. Trig is right triangles. And if you have 9x squared plus 1, would you agree that this side could be 3x and this side could be 1? And if you did the Pythagorean theorem with 1 and 3x, wouldn't you get 1 squared plus 3x squared, or 9x squared? Now, I would assume half of you put the 3x where I put it, and the other half of you put it in the other location, and it doesn't actually make any difference. But wherever you put it, you still got to stick an angle in here. I'm going to put it right there. So I now see that tangent of theta equals 3x over 1. Notice that's a nicer choice. Had I put the theta in the other spot, I'd have 1 over 3x. And since this is 3x over 1, it's just really 3x. The tangent of theta is 3x. And so that's nicer algebraically. I'm sure it would work both ways. But again, what you need to see this as this is your converter between the two worlds. This is how you get from the world of x to the world of theta and back again. It's everything you need to tell how something in one world is something else somewhere else. And all of a sudden I see why they chose 1/3 to 0 for the limits of integration. I didn't know that before, but now I do. If you screwed that up, I'm going to also give you another little bit of time here to get on the right path. While you're doing that, I'm going to cheat and go over to Desmos and actually ask it the answer to that. I'm going to ask, since this is a integral, if I was an engineer, I wouldn't be doing any of this. I'd just cheat and type it in. So I'm going to go over to Desmos and do that so we have the right answer. So I got 0.2357.
So how did you get 3x?
Because I saw 9x squared plus 1 as the Pythagorean theorem of something. In other words, something squared plus something squared. So if I took 3x and squared it, I'd get 9x squared. If I took 1 and squared it, I'd get 1. And so if I did the Pythagorean theorem to 3x and 1, wouldn't I get 9x squared plus 1? Isn't that what I would get up there?
Yes.
And so that's what I saw in the original problem. I said, hey, doesn't that 9x squared plus 1 square rooted? That looks like the Pythagorean theorem. And so that's referencing a right triangle. And so again, I'm making an incredibly surprising substitution here. I'm doing this on faith, frankly. Like I don't understand it. I just see that Pythagorean theorem exists. And
wouldn't it still be that square root of 9x squared plus 1 to the third power?
Yeah, and so you're right. Like maybe that third power is bothering you. Isn't it weird that this actually works? Like I would have expected that just to be the square root of 9x squared plus 1. And yet it's cubed. But remember, if I replace that whole thing with something nice like u cubed is fine. Doesn't matter if it's cubed. So it's u cubed. Great, I can handle that. The point is the plus sign goes away, right? Well,
Totally.
if the plus sign went away, and not only that, if I could square root it, because then if I could do that and I have something cubed, hey, I'm home free.
That makes sense. Thank you.
I'm hoping they were, somebody thought about this. If I make up a random problem, I usually don't look in the book for problems, but this is a section where I got to be really careful. If I make my own problem up, it could be really difficult. All right, so I'm going to catch up to you. Let's see, what do I need? I'm switching out all kinds of stuff here. I've got these x's to switch out. I've got this x to switch out. I've got that x to switch out because I'm trying to get into theta land here. So let's go do that. So let's use our converter. So one thing I'm going to need is dx's. So if I take the derivative of the tangent of theta, that's terrifyingly secant squared of theta, d theta. And the derivative of 3x is just 3 dx. And notice I need to replace dx. So I'm going to solve it for dx. I usually don't do this because you should be able to see this in your head. But dx is equal to the secant squared of theta d theta divided by 3. And so that's something I'm going to need. I now have a way to switch out dx. And I secondly know, since I've got an x over there, I secondly know that x would have to be equal to the tangent of theta divided by 3, or 1/3 tangent of theta. And so there's another thing that I'm switching out. And then lastly, those limits of integration. So if x is 1/3, if x equals 1/3, then I guess that would mean the tangent of theta equals 3 times 1/3, which is 1. Again, you should know the answer to this from the unit circle. If the tangent is 1, then doesn't that mean the triangle has 1/1? The tangent of theta is 1/1. What angle is that?
45 degrees.
45 degrees. or square root of 2 over 2 on your unit circle. I don't know if the book is asking me for an exact answer for this, so I'm going to give the radian answer to this. So I see why they picked a third now. I was thinking, why would you pick some weird number like a third? I would have picked like 5, and that would have seemed nice, but then it would have ended up terrible. And then I also know, so there's another conversion that I need. And then lastly, I just need to know what about 0. And so 0, if x is 0, then I'd have the tangent of theta equals 0. Ooh, can you pull that one off? Where am I? What angle am I at? If tangent is 0, do you speak the language of trig well enough to pull that off? It's a hard one.
Is it 90?
90 half pi.
Think of it this way. Isn't tangent sine over cosine? When is a fraction equal to 0? If I have a fraction that's equal to 0.
When the denominator is 0?
Close.
Where it's pi, or 2 pi or 0.
When it's the numerator is 0. So like 0 divided by 5 is 0. If the top number is 0, then it'd be 0. So the question is, when is sine 0? And the answer is right there.
2 pi.
So 2 pi or 0. 0 is an easier answer. Now again, let's say that you forget that, or you don't know that. Can't you just say inverse tangent of 0 on your calculator? Like, use a calculator. So don't I now have all the ingredients I need to switch my problem into theta land? And so let's see if we can pull this off. So now we're saying that it is no longer the integral from 1/3 to 0, but rather the integral from the square root of 2 over 2 to 0. It's kind of interesting that 0 stayed 0, isn't it? Isn't that kind of interesting? And then I have 1 over the square root, well, not really the square root, 9 times x squared, 9 times x. Well, we said here that x was the tangent of theta over 3. So 9 times the tangent of theta over 3 squared plus 1 to the 3/2. Can you see what's cool about the bottom right now? Can you see where that's going? Again, it looks terrible, but where's that going? We'll get there. And then times dx, the last thing, and I figured out right here that dx was secant squared d theta over 3. Again, success. I could go into Desmos right now and type that statement in, and I'm also going to get 0.2357. But that is a terrifyingly large statement to type in. As I said, these problems get worse before they get better. This looks like it is not going to work. It looks crazy, which is why you need to be taught it, because you would never think to do this.
Well, the secant squared is equal to 1 plus tangent squared. And then when you're multiplying those things together, shouldn't they cancel?
Yeah, watch what starts to happen now. On the bottom here, you have tangent of theta squared over 3 squared, which means you have 9 tangent squared over 9, which means you just have the tangent squared. Ah, I see now, you should say, if you did not see this before. I see what happened here.
I think you meant to write a 0 instead of a 2 at the bottom of the.
Thank you, Justin. So isn't tangent squared plus 1 equal to secant squared? And then the fact that I still have this terrifying secant squared out here is all of a sudden not such a bad thing, is it? Because I can now say bam, bam. And so this integral just turned into, wait a second, I can't do that, can I? I ignored the 3/2. That's not just secant squared, it's secant squared to the 3/2. So I got to slow down a little bit. I got a little too excited there. So let's rewrite this and see what that means. Let's see. So there's a 1/3 here. So I think I'll pull that out front because I don't want to be confused by that. And I have 1 over the secant squared, but that's also raised to the 3/2.
You still have the +1 in front of the, oh no, never mind.
Good. Think out loud. Good for you. I'm thinking.
Can you separate it and turn it into a secant squared theta times a square root of secant squared theta?
Yeah, how do exponents work? If you had x to the 7th to the 3rd, because isn't that what we have here? We have a power raised to a power. What do you do with those powers? What can you do with those to kind of clean that mess up?
You multiply them together.
That's exactly right. So in this case down here, that would be x to the 21st. So if I have secant squared times 3/2, squared times 3/2 would be cubed. So that is actually just, to save a little bit of space here, I'm just going to say this whole thing is actually secant cubed of theta. And so I have secant squared over secant cubed. Which would be 1 over secant. And in some respects, I'm on the edge of my seat because I'm hoping that this integral is easier, right? Remember the original integral, although it looks simple, it is not. And I just changed it into thetas. And when I first did it, I thought this is idiotic. They're in green. And yet when I started to do the algebra, all of a sudden I got to here. And the question is that easier? The answer is very much so, because what is 1 over secant?
It's the natural log, right?
No, easier than that. You'd have to let u be secant of theta.
Oh, it's cosine.
Yeah. So I want you to think about what Justin's first instinct was there. Like your first instinct to that very well could be, oh, the answer is the natural log of secant of theta. But you would have to, in order for that to work, you would have to let u be the secant of theta. And then du would be the derivative of secant is secant tangent. Like there's more to that. You can't just say the answer is the natural log of secant of theta, because this is a chain rule problem. There's junk inside of junk. You have a fraction, 1 over secant, and then you also have, or 1 over something, and then you also have the secant of it. So there's 2 things going on. So the answer to that won't just be the natural log of secant of theta, I'm done, which is very tempting. So if you notice, again, would you agree this is a substitution? If I rewrite that as cosine, that's a substitution. I just didn't substitute it to a new land. I'm still in theta land. And so now for the first time, I'm like, oh my God, I'm done. The integral of cosine is sine. That's so awesome.
Negative sign.
No, not this time. That's an easy mistake to make.
Oh, yeah, I was going the wrong way.
Yeah. So we're going back and forth so much, like to screw up the negatives. Like you just watched me do it a minute ago. It's super easy to do. So the derivative of sine is cosine. Like I almost have to stop and think about that. The integral of cosine is sine because the derivative of sine is cosine. So then I throw in a pi over 2 and a 0. I said pi over 2, but square root of 2 over 2. Actually, I did something else dumb that none of you corrected me for, that I should have fixed along, that I should not have done. What's wrong with that statement right there? Didn't we say theta was 45 degrees? And what I gave, instead of the angle to get you to 45 degrees, I gave you the X and Y coordinates. I gave the coordinates of that location, not the,
Right. Wouldn't it need to be pi over 4?
exactly. And the reason I just noticed it is because I realized I'm about to take the sine of the square root of 2 over 2, and I'm like, you can't take the sine of sides of a triangle. And so then I realized, oh, you did something dumb earlier. So rather than erase it, I'm going to go back and.
I was gonna say something when you said that the tangent, or when we did the x equals 0 part, it felt like they were two different answers from different parts of like the same thing. You know?
Yeah. As I've told you many times, I like making mistakes of that nature because I've taught trig probably 50 times.
Would that mean that also the 0 coordinate would need to be 2 pi, right?
No, because 0 and 2 pi are the same angle. And 0
Okay.
is the way to say it. So now
So does that mean essentially if you did plug in 2 pi, would you get the same answer?
Yeah, you would, because we're about to take the sine of it, right? If you take the sine of
Right.
sine of 2 pi, you're in the same location.
Totally, yeah, that makes perfect sense.
So if I take the sine of pi over 4, you look on your unit circle, that's the square root of 2 over 2. If you take the sine of 0, you get 0. The sine of 0 degrees is the y coordinate of the angle of 0 degrees. And so the answer is exactly, apparently, the square root of 2 over 6. Again, I say apparently because what's the chances I just did all that right? I caught one of my mistakes. You caught, I think, 2 other ones. But, you know, what I'm hoping now is that if I divide that on my calculator, I get 0.2357 because I already know the right answer. Again, engineers would have been done hours ago because they would not have wasted all this time. They would have just got 0.2357 and went and built the bridge. But as I often say, none of you looked at that and said, isn't that the square root of 2 over 6? Like, I think I recognize that. Like, none of you recognize that, right? At least I didn't. I can't even remember. Was that the answer? Yeah. So I'm on the edge of my seat now, having checked my work, hoping that that is really true. Square root of 2. And if I didn't catch my mistake earlier, I would have caught it here because it wouldn't have got the same answer. Yeah. Can't believe it. 0.2357. Check. I love that. So lots of you guys are doing this on your task now. You're like, checked in Desmos. Love that.
It's awkward when I check it in Desmos and it's still wrong though.
I have gotten a few of those.
So Doug, I have a quick question just about the X limits. I guess I'm not really understanding. Why is X 1 over 3? And then I just don't quite understand how he did that.
Yeah. So in the original problem, the fact that there's a 1/3 and a 0, and the fact that we're working with X's implies that they're telling us X is 0 and X is 1/3. Those are X values because we're working with X's. So you don't usually write it there, but you got to think to yourself, hey, those are X's. And now we're saying, I need those to be thetas, right? In other words, we need this to say, and this is how I could have caught my mistake. If I'd have said theta equals the square root of 2 over 2, I might have thought, well, that doesn't make any sense. That's not an angle. What am I doing? So those are thetas. I need thetas. Okay, well, then I come back here and I say, okay, well, X is 1/3. Well, what's my converter? That's why this is such a powerful concept and why I put a cloud around it. That's my converter between the two worlds. So if X is 1/3 and you throw 1/3 in there, then don't you get 3 times 1/3 is 1? So I get tangent of theta equals 1. And so now I got to figure out what value for theta. I got to figure theta out.
Okay, that makes way more sense. Thank you.
Good question. It's hard, isn't it? It's like, man, it's not hard, but you actually really got to know everything you've ever learned. And, you know, one problem takes 2 pages. I mean, this is crazy. 1.5 pages. Both of these
I
problems.
feel like somehow my algebra is still lacking for this.
Yeah. Yeah. That's why I've warned you guys about this the entire year, that calculus is not hard. This problem is not hard. It's just, you really got to know algebra well. You got to let algebra do its work. You got to go slow. If you try to memorize anything here, you're never going to get this. That's why what I said over here, I think, is so important. Kind of that language of, this is my conversion. This statement right here, that tangent of theta equals 3x, that I stole from the right triangle, thanks to the hint that I'm in chapter 8.4 of the book. That purports to be my converter. And then I look back at the problem, all those orange highlights that I made, and say, dude, I got X's everywhere, man. I got to get rid of all that stuff. And notice, it's extremely important to notice the dx, because that dx came with a giant pile of stuff. You can't just say, we don't need dx, get rid of that thing. Later on in advanced calculus, if you stay with me, we're going to talk about that a little more deeply. There's an amazing concept that is waiting for you, that Eve miraculously figured out on her own watching videos, called the Jacobian. But
it's actually really fascinating. Like the YouTube channel I showed with you, the guy like goes through like linear algebra, and then he starts mentioning the Jacobian. It's just incredible. Yeah. What's especially incredible is that people come up with this and they have to prove it's right. So the amounts of proofs that he goes through is just insane.
Yeah, so true. In other words, as is often the case, this is not the end in math. That's the only reason I'm even saying this, because you obviously don't understand what we're talking about here. But this turns out to be a shadow. I mean, you think, what's a shadow? It's when the sun shines against an object. Think about a person. You see a shadow of a person on the ground, but it's like, how much more amazing is the actual person in color and feelings and thoughts and wishes than just the black and white shadow on the ground. And even what we're studying right here turns out to be a shadow of something that is three-dimensional, if you will. We're looking at two-dimensional math here. We're trying to find the area under a curve. That's all we're doing. Find the area under a curve. That's a two-dimensional problem. But there's 3 dimensions, and mathematically you don't even stop there. There's 4, 5, 6, 27. We can't necessarily conceptualize of that, but this actually is terrifyingly and beautifully just scratching the surface of a concept. So hopefully you have some reason to take Calc 4, because it's,
yeah, I was actually gonna say, is that Calc 4 or 3?
Yeah, it's 4. So my point in this is, you really have to let algebra do its work. Again, I like to think of algebra as a language. If you go to some foreign country, if you don't speak the language, you just can't get stuff done. I can't keep this straight. Like this problem is these are way too big for be like step 1, step 2, step 17. Like you just can't do it. You just got to let algebra do its work. So the fact that I said, here's my converter, hey, look at all the orange junk I got to switch into X's. So then I wrote 1, 2, 3, 4 over here, where I made something that replaced every single one of those. I wrote that down in green, and I thought, this is a stupid idea. This can't possibly work. And yet, as I start messing with algebra and trusting the process, it goes from green to blue, and then blue to red, and then red to green. And then all of a sudden the integral is the integral of cosine. Wow. What a breathtakingly brilliant substitution that is. Who thinks of this stuff? It's not me. For a test question, I would say this is a good test question. The reason is because when you got it simplified down, it wasn't terrible. Like if that had came out cosine cubed, I taught you how to deal with cosine cubed, sort of. I mean, we haven't practiced it a lot, but I taught you how to deal with that. But that's, now it's like, oh, great. Now now all of that work to just get it to be a chapter 8.3 problem. And then I got to start all over again and make some other substitution again. So in my opinion, on a test, I should give you a question just like this and say, use trig substitution as a hint. And when doing so, you actually get an integral that you can just take and you're done. Integral of cosine sine. Awesome. I'm done. I don't have to make some substitution again. And that is what would have happened had I made this problem up. And notice that did happen with the circle. We got all the way down, and what did we get? the integral of sine squared. And so we still weren't done. Do you see what I'm saying? We still had to think about that. That wasn't obvious. The integral of sine squared is not obvious. I still have work to do. I've got to do integration by parts or substitution, or got to do something else. Not good. It should feel to you like a good test question would be one question. Do you agree with that? Let's give you 2 hours, so you have plenty of time to do dumb stuff like I just did. You have plenty of time to like check your work, go to Desmos, get the right answer, and then, you know, go work through the math and, you know, make foolish mistakes and fix them. And but I think you would agree that if I got all finished and I got this wrong, like it wasn't the right answer, then I would have to stare back at what I did. Wouldn't that feel really overwhelming to you? Like if you got this wrong, like, oh no, now where do I look? Because remember, your mistake could be dumb, like mine was. The angle is square root of 2 over 2 instead of pi over 4. That's sort of a dumb mistake. Understandable, but dumb. And I did a number of other dumb things. I forgot the 3/2. I made some negative mistake that one of you caught. I forgot. But it's like really daunting. And notice, you know, I'm the teacher of this, but how many mistakes did I make along the way here? Like 4. So when you look back at it, it's not like you made one mistake. You probably made 4 mistakes. And so, woo, this is daunting. We are way out in the universe here.
So, real quick,
Yeah, go ahead.
in the very first, up there at the top, at the beginning of the problem, it's written as 1 over the square root of 9x squared plus 1. That's the hypotenuse, right?
Yeah, because of the plus sign. You understand that? Because it's a plus sign, I was adding them. For that reason, I knew that the 3x and the 1 had to be the 2 legs of the right triangle. If there's a minus sign, like there was at the start back here, if there's a minus sign, then I know that the positive one has got to be the hypotenuse. Does that make sense?
Yeah.
And then you're subtracting one of the legs. And so I know the x is one of these 2 sides over here. I just don't know which one yet.
Yeah, because I actually started out by labeling my triangle with that square root expression, and then I did like sine of theta equals 1 over that whole thing, but that was really ugly. And then you mentioned using 3x, so I switched to using 3x, and that made it a lot nicer. But like if I had continued with that hypotenuse, would I be able to do like get to the same answer?
Let's see. I might have to, that's probably a fairly big answer. I mean, I think the answer is yes, if you don't make an algebra mistake. So in other words, what you're saying is you wrote in the green answer, and then you said, hey, I think I'll use sine. Sine of theta is 3x over the square root of 9x squared plus 1. Or maybe I'll use cosine. Cosine of theta is 1 over the square root of 9x squared plus 1. Yeah, I think it would still work, but I'll have more algebra to do. So
yeah, there was way more.
Simplest sides. That's kind of what it comes down to. And notice the 2 sides I'm picking are the sides that I see here. In other words, isn't there a 3x and a 1 right there that are being squared? It's like that's the 2 I want to use. Don't use the complicated one. That's a great point you make.
Yeah, that makes more sense to like look under the square root and see, you know, check for a simpler substitution.
Let's set one more up. Maybe we won't have time to completely solve it, but I'm just kind of looking through. Let's see, this is question 54. And it actually looks easy. But it's question 54, and there's like 53 questions before this. So I'm kind of assuming they put them in a little bit of order. So I'm wondering if this actually isn't easy. Would you agree you might be tempted if this wasn't in this section of the book or you weren't warned, you might be tempted to let u be equal to y squared plus 1? That would work awesome if that 4 wasn't there because the derivative of y squared is y. That would be great. That's an awesome substitution, super simple substitution problem. But unfortunately, with that 4 up here, that's not going to work. Now, could you transform this into an equation with u's? Absolutely. But the question is, will it be easier? That's the problem. Let's quickly do that. So let's see, this would be du equals 2y dy. And so let's see, I have y to the 4th up there, and I have u down here because y squared plus 1 is u. And then I got to replace dy with, well, dy over here. So I have to divide 2y over. So this would be du over 2y. So that's kind of cool because this y cancels with one of those y's, but I still have y cubed. Does that mean we did it wrong? The answer is no. Can you get y cubed from this? Again, you got to go over to your converter. Isn't that your converter? Now, unfortunately, I wish that said y squared. If that said y squared, not y cubed, then actually I think we would have been able to do this. So if that y to the 4th would have been a y to the 3rd, I think we could have been able to do this. But let's see, that would mean u minus 1 equals y squared. To be cubed, wouldn't I have to raise both sides to the 3/2 power since you multiply exponents? So now it's y cubed. So then I have not y cubed, but u minus 1 to the 3/2 over u. There's a 1/2. Bam, success. Followed by failure. What's the failure? I can't do that. I can't take that integral. And again, it doesn't mean this won't work, but I guess my next thing I would try is let w be u minus 1, or I don't know what I would do. I'm not sure what I would do next. But notice this transformation just turned into almost the same problem we did a minute ago. See how it's u minus 1 square rooted? It kind of has that Pythagorean look. Well, except for the fact that that's not u squared. So maybe that isn't Pythagorean theorem. But you see what I'm saying? Like if I was just given this problem, you know, say a few months from now when this all wasn't fresh in my mind, that's exactly what I would have tried. I would have tried that. And yet that didn't work. So because this is in chapter 8.4, because on a test I say use trig substitution for this, that would save you 20 minutes, wouldn't it? Might save you an hour. Are you getting the feel? So what you should do is say, hey, y squared plus 1, that looks like a right triangle where one side is y and one side is 1. And as Cheyenne just astutely pointed out, I don't really want to get the hypotenuse involved, which would be the square root of y squared plus 1. That's true. So I could make a trig expression for sine, cosine, or tangent, but I want the easiest one I can possibly get. So you tell me this, where should I put the angle and what trig function should I use to make this the easiest I could possibly make it? Here is not here. Why? Go ahead, Justin.
Never mind.
Was that what you were going to say? Why is it easier to actually choose this angle to label?
Because then it's just y. It's y over 1.
Yeah. Then it's tangent of theta equals y over 1, or just y. If I did it the other way, it would have been the tangent of theta is 1 over y, and then I wouldn't have had quite the simple of an answer. You see that? It doesn't mean it won't work. I want life to be easy. So this is my converter. Tangent of theta equals y. This is my conversion between the two worlds. So I'm trusting the process here because that just doesn't feel, that just feels really weird. So I'm gonna let you go pretty fast here, but at least want to get it set up. I'm gonna stop once I get this thing set up. And so great, I got things that I need. So I also need dy. So the derivative of y on the right is the derivative of tangent of junk is secant squared of junk times the derivative of the junk. And so there's a second thing that I need. And so I think I have everything I need now. So can't I say that since I know what y is, I can say, well, the top then would be tangent of theta to the fourth. The bottom would be y squared plus 1 tangent squared. Ah, I see why they did that, because that's secant squared. And now I don't have the plus sign down there anymore. That is brilliant. We hate plus signs on the bottom, and that just got rid of it. Wow, that's amazing. And then I've got to replace dy, which I just discovered was equal to secant squared theta d theta. Success. Success followed by success this time. Doesn't look like it. Every problem's the same. Looks worse before it gets better. But I can see already that this is just secant squared. And then all of a sudden, because I don't have any exponents like I did a minute ago, that cancels with that. And so now I have it down to tangent theta to the fourth. But notice, yeah, no wonder this is question 54. I'm still not out of the woods. Tangent to the fourth is no joke, right? That's like an 8.3 problem. So I just did all that work, and now I got to like go back to 8.3 and see if I can figure out what the integral of tangent to the fourth is. No joke. So
Even numbers are the beast, right? If it was odd, it'd be easier.
yeah, that's right. That even odd thing. So again, I have all kinds of options. Like I could replace tangent squared with secant squared minus 1. So I'd have a tangent squared times the secant squared minus 1. And honestly, I have to play with this personally. Like I don't practice this enough. I don't want to be that good at it. I think it's kind of fun to play around a little bit. Like I'm not sure. Or I might look, remember I showed you that power reducing formula? So I might go, which was integration by parts. So I might split this into tangent and tangent to the third, or perhaps tangent squared and try integration by parts. Like, so
That was my suggestion.
I'm not out of the woods here, but it's gonna work is kind of the point. So, yep, good job, authors. I can see why you put this as question 54. I don't want to do that on the test. That's not good. All right. I'm gonna play with this some more, just because I'm curious. And as I said, I don't know the answer. So I found myself thinking, I kind of want to know how to do that. So I'm gonna play with it. But I'll just stay on Zoom to do so and talk out loud, but it's 9:24, so we'll say I'm getting you out of here 6 minutes early because it's usually 9:30. Let's see. More importantly, if you have a question, like that's what this time is for. So if you want to ask me something about 8.3 assignment or whatever you want, like that's what this time is for. So integral of tangent is like natural log. That just seems like a terrible idea. Tangent squared, let's see. Tangent squared plus 1 is secant squared. So that means tangent squared is secant squared minus 1. Assuming I'm going to have more than one trial. So I'm thinking about integration by parts, and I'm thinking, unfortunately, the integral of tangent, if I remember right, was not that nice. It was like natural log of cosine. So I'm thinking integration by parts with tangent just sounds terrible. But I'm wondering if I switched out tangent squared for secant squared minus 1, and I had 2 of them. So that's tangent squared times tangent squared. The reason I'm wondering if that's not a good idea is because the integral of secant squared is tangent. That's nice. The integral of tangent, not nice. I wonder if the integral of tangent squared is nice. I don't remember off the top of my head. Oh, actually, yes, I do. The integral of tangent squared. We made this in class the other day because that's the integral of secant squared minus 1. The integral of secant squared is tangent, and the integral of 1 would be theta. Or x or whatever. So now I'm rethinking my idea. I don't know, I'm going to progress with this. This seems kind of fun. So let's call that v and v prime u. So if u is secant squared, the derivative of, oh boy, this is horrible. This seems like a terrible idea. Derivative of secant is secant tangent, so I don't know, these are ugly. Maybe I won't quit so soon. So let's see, u prime would be the derivative of junk squared is 2 times the junk times the derivative of the junk. Derivative of secant is secant tangent. And the derivative of 1 is nothing, okay. The integral of v prime, the integral of secant squared is tangent, so that's why I think this might not be a bad idea. And the integral of 1 would be theta. So let's see, does that create an integration by parts that actually makes my life easier? So I have uv, so secant squared theta minus 1 is u. V is tangent of theta minus theta. There's uv minus the integral of u prime v. Woo, this does not look good. U prime would be 2 times secant times tangent. So there's u prime, and then v is tangent of theta minus theta. This looks terrible. This does not look good. Unless a bunch of stuff cancels somehow. Feeling like trial number 1 is a failure. That did not work. Not sure, but seems worse. Tangent is sine over cosine. Secant is 1 over cosine, so that's going to be cosine cubed. That just seems really ugly. Trial number 2. I'm going to think of this as the integral of tangent squared times tangent squared. And let u be 1 and v prime be the other. So the derivative of junk squared is 2 times the junk times the derivative of the junk. Notice I switched to x's. The integral of tangent squared, we said a second ago, was actually just the tangent of theta minus theta, tangent of x minus x. So let's see what integration by parts says about that. U times v. So I have, oh, that looks nice actually. That looks pretty nice. I have tangent squared x times tangent of x minus x minus the integral of u prime v. Oh, that doesn't look good either. 2. I'll put the 2 up front. Tangent of x secant squared of x times tangent of x minus x. Woo! Don't like that. Let's not give up just yet, though. Let's see, let's just look at that. So that's the integral, if I multiplied it out, of tangent squared. If I multiplied this in, that'd be tangent squared times secant squared. And then minus x times the tangent of x secant squared of x. Man, it just seems terrible. Part of me wants to quit because I think that's terrible and it won't work. Part of me wants to continue. If I did replace secant squared, with tangent squared plus 1, then I'd be multiplying tangent squared by tangent squared, and I'd have the integral of tangent to the 4th, which I already had and couldn't do. This feels like a dead end. Trial number 3. I'm going to split this into tangent of x and the tangent cubed of x. Maybe that's the way I should be splitting this for integration by parts. Now I have a difficult choice to make. Which one is u and which one is v? Let's see, which one of those would be easier? The integral of tangent cubed. Is that easy or is that hard? Well, it seems like it's going to turn into tangent to the 4th. So my gut reaction is that's terrifying. I'd rather take the derivative of tangent cubed. So I'm going to try that. So the derivative of junk cubed would be 3 times the junk reduce the power of that, and then times the derivative of the junk. Derivative of tangent is secant squared. So that's kind of ugly. And then v would be the integral of tangent, which we said before was tangent of x minus x. I hope I haven't been doing that wrong the whole time. Double check the integral of the tangent of x. Why isn't it listed? Is it really hard? Oh yeah, I got it wrong. The integral of tangent of x is not tangent of x minus x. That's the problem. The integral of tangent of x is negative natural log of cosine. What am I doing? That's not good. That means everything I tried was not true.